Hi, thanks to the organizers for having me. So this is supposed to be a very novice talk, and the point of view I'm going to take is more almost like an evangelical point of view. So I'm not going to go to huge depth into the whole random forest algorithm or so, but it's more I'm going to use it as a case study as to why now starting on data analysis is so cool and empowering, and how in the whole language wars, there's really not really a point for language wars, but more about, okay, there's so many different tools, let's just make our own bag of tools bigger. So I titled Random Forest R versus Python, but it should be more like R and Python. So here's a big disclaimer, I'm not a Pythonista. Actually, I'm very new to Python. I'm very much an R user. So this was more an exercise on how to have fun when starting out in data analysis. So that is my surname, and that's why Ian was having trouble pronouncing it, because it has so many U's. So I've
got a Z and an S and a V.
I know, but OK. So my name is Uruchurtu. You can find me on Twitter. That's my favorite social network. My friends make jokes that I tend to be faster answering via Twitter than any other way, including phones. And I currently work as a consultant at DVI, which is a web analytics and data consultancy. And I'm a physicist by training. I'm a reformed string theorist. So yeah. So this is the outline of this talk. First, I'm going to give you a motivation as to why I'm going to be talking about random forests, and in particular when it concerns to R and Python. Then I'm going to go and discuss random forests and their implementations in R and Python. And I'm going to focus on a very specific example, namely the ME music set. And I'm going to tell you a story as to why this is an interesting example. And then I'll give you some concluding remarks. So motivation. So when you're starting out in data analysis, there can be too many resources. You go online, you go on Twitter, maybe follow people that do data, and just go like, oh, this guy says Python is the best thing, or R is the best thing, or like, what the hell is the best thing? So it can be quite crowded over there. You go to GitHub, there's so many different things. You then go and take maybe a bunch of MOOCs. So you go to Coursera, you maybe have done several Coursera's. Each of them might have your favorite language. In this case, they can have Python. There's others in Java. They can do R, etc., or MATLAB. Then you go to Kaggle, and you can, if you are into Kaggle competitions, you can find huge threads saying like, oh, I did it in R because this is awesome. So quoting from the previous speaker, yes, awesome is a word that you find a lot online. And then also Stack Overflow, favorite website for figuring out how to do things. Then you can also go to books, or maybe if you went through the school academia work and you happen to do some technical degree, maybe some courses, they picked Python or C or C++ or anything to teach you how to code. So that's what you know, and that's how you start doing things. So the popular question is, which language should I use? So if you go on Google and say data analysis language, you'll find these are the top results that I found when I did this search. So I found R, and then you have huge threads, and then MATLAB, and Julia, and of course Python somewhere over there. So this is my own experience. You start by what you know, and you ask your friends. So my first language programming was in C. So I was first year of uni, and that scared me to death because I thought it was super complicated and sort of put me off for a while. Then I started using MATLAB, and I was like, OK, somehow I like this. Then I spent a long time playing with symbolic languages, Mathematica and Maple. So, and then I was like, I actually like doing this. And P.S., I had not met the IPython notebook. And if I had met the IPython notebook before, I would have been much more positive about programming at that stage. So I don't have a web developer background. And then because I did maths and physics, I was surrounded by people doing stats. So then you pick the right tool for the task at hand. And that's why this is the big reveal. I'm an avid R user. So for me, going from Mathematic and Maple, jumping into R was sort of a smooth transition. And it was much later when I found all these threads online saying like, oh, the syntax is so horrible. Like, why would you do that? And I'm like, no, it's nice. So this leads to the whole language wars. So there's too many articles about Python displacing R as a programming language for data analysis. Is Python really supplanting R for data work? 10 reasons Python rocks for research, yay. Why I'm betting on Julia. And these are all legit articles. You can go and find them. Why Python with coffee is better than R with ice cream. Actually, that's that there. Well, TLDR. So it can be very confusing for a newbie. So this is pretty much the gist of it. Insert favorite language is better because I say so. Well, OK. However, I think it is good to have a general understanding of the pluses and the minuses of the various data analysis tools in order to pick the right tool for a job. So for instance, R has everything you need for performing statistical analysis. There's pretty much a library for everything you can think of, and even several libraries for the same thing. So there it goes more into, OK, which of all the libraries does better the task that I want to perform. Then R, MATLAB, and Python are great for prototyping. Python is a full-featured programming language, so it's easier to incorporate Python outcomes into a full data product workflow. So each language has its pluses and its minuses. So it's good if you're a bit of a polyglot, then you can talk to people that work in specific languages and maybe learn 1 or 2 lessons. So I think that it's better to spend time defining the problem and determining what is the best way to solve it. So for that, it's very good to have a big bag of tricks. So I started dabbling on Python probably later, like October last year. And I was going online, and I found this very nice website, or this blog, called Slender Means. And it has this awesome section called Will It Python. So this is someone who is an R user, and his task to teach himself Python in data analysis is to redo, well, he started redoing the machine learning for hackers, all the R code, but in Python, just to see what I can learn from Python, or maybe there's a better way of doing things in Python compared to how I do things in R. So I said, OK, I'm going to take this approach with a small project that I did in R and try to do it in Python and see what lessons I can learn. So for that, I use the scikit-learn library, which is the library of machine learning algorithms. It's open source. It has an API. Basically, it amalgamates and connects with all the other Python libraries, NumPy and SciPy and all the other things that finish with P. It's accessible, has many models, documentation, and examples. So this is pretty much a great, great resource for someone who's just getting to grips with it. Yeah, so it is pretty awesome. I also use the word awesome a lot. So I guess for the great events in life, then I would use super awesome. So anyway, this is my example. So let's choose a problem. So it's always a good idea to look for a data set that is interesting to you. So if you're starting in data analysis, and you're really serious about it, it's probably a good idea to pick a set that really inspires you to ask questions. So once you choose a set that is interesting to you, you formulate a question, then you formulate an hypothesis, and then you probably build a model to answer the question and test it. Well, test your hypothesis. So this is the scientific method for the win. People have been doing it for a long time. So let's follow this through. So choose the data set. So an interesting data set that you can find online is the MUsic 1 million interview set. It's in Kaggle. It was also the subject of a hackathon a year ago or 2 years ago. It's one of the largest preference data sets in the world. The extract is in Kaggle, and it's available as 4 separate data sets in CSV. So the 4 data sets are a train and test set, which includes artist information, track information, user ID, time, and ratings. So this data set pretty much pretends, basically they just ask a bunch of people, sat them down, presented them with a series of songs, and asked them to say if they liked it or not. And then they also had to answer specific questions about behavioral questions, demographics, etc. So it's quite a rich data set. So for instance, the second set that you're presented with, the words data set. So you have a set of 82 adjectives. So every time a person was sat down to listen to a song, they asked this person to use the best words to describe the song. So say maybe if they put you like the latest Rihanna hit, you will say that it's upbeat. So then you put like 1. And if it was, not romantic, you would put 0 or 1, depending if you thought it was romantic or not. There was also questions about if you actually own music of this artist, or if you have heard music of this artist, and etc. So this is contained in this data set. And finally, demographic information, such as gender, the age, their working status, the region. This is all pretty much in the UK. Also, some specific facts about their behavior, such as how many hours per day on average do they listen to music, if they listen to music that they own versus music that they don't own, and they might be streaming online, etc. And then they were also presented another set of questions where they actually had to rate themselves from a scale from 0 to 100. And these questions had to do with the fact of how much do you agree or disagree with the statement. So, for instance, you would have a statement such as, music is important to me, but not necessarily the most important. So how much do you agree or disagree with the statement? And pick 1. I like music, but it does not feature heavily in my life. Music is no longer as important as it used to be. So rate yourself, give some number, and there you have a lot of stuff. So this is actually a not very sophisticated visualization of the word set. So you have all the different entries, rows, by user per song, user ID. And then if the word, each column is if the word was used or not and how many times. So for instance, you have words such as uninspired, aggressive, unattractive, boring, cheap, irrelevant, way out, annoying, cheesy, unusual, outdated, unapproachable, etc. So 82 adjectives. And of course, there's lots of sparseness in this matrix. And then you can also look at the word use across artists. So there's actually some words that were very heavily used. And if you identify these sort of bright spots, these adjectives are used a lot with regards to specific artists. So wholesome, all legendary, pioneer, dark. So maybe it must be someone like, I don't know, Bob Dylan or the Beatles. Unfortunately, we're not prone as to which artist is referred to because it's just encoded with artist ID. But then you can speculate. And finally, the user's data set, like the 19 music avid questions. So these are the typical statements. I enjoy actively searching for and discover music that I have never heard before. From 0 to 100, how much do you agree with this or not? I'm not willing to pay for music. I like to be at the cutting edge of new music. I love tech, etc. And finally, this is a distribution of ratings. It's just the histogram. And something that is very interesting is that actually the rating seems to be very highly clustered. So you know how we are in all this culture about the 5-star rating thing? So this makes pretty much good evidence as to why 5 stars actually make sense. So this is more or less how it looks like. And so why is this data set interesting to me? Well, I grew up with music. My dad loves music. I'm very interested about how technology has disrupted the music industry. So I found this infographic online which says how your father's favorite music indicates what you listen to today. This is so true. So yes, I guess this is pretty much good sort of psychological motivation. But also then, if you look at the landscape, how technology has disrupted the music industry, you can see that this has happened at 3 levels. So you have production level. Now it's cheaper to produce. There's lower barriers to entry for budding artists. The distribution, internet has made music more accessible. Artists can decide where and how to sell. And finally, consumption. So people's listening habits have changed due to the internet and to the change in devices. So now, my question to you is, like, how many questions can you think with respect to this data set? There's many different problems that you could think of trying to get backup for your statements from. So let's look at specific problems. So for instance, if you're an artist, now it's easier to produce music, but it's harder to make yourself known or earn a living. For record companies, people buy per song. It's easy for a listener to consume without paying. So the competition field is wider. And then for the listeners, there's too many choices. Discovery is difficult. So if you had all this information about people's music habits or listening habits, how can I make use of this information in order to help me solve this type of problems? So questions that may arise is, for instance, can you predict the rating of a song? So this might be useful for discoverability, for specific engines that might suggest you that if you like this, then you like this. So as part of collaborative filtering problems, what factors are important to determine how much a person likes a song? This might be important for marketing departments, also to know for record companies to know which musicians they should be considering and presenting to people so they buy records and they generate more revenue. Or what is the minimal set of factors that are needed to determine how much a person likes a song? It's like, can I reduce this hugely highly dimensional problem to a smaller problem and then find exactly what are the triggers behind why a person would like a song? So this is just 3 different questions, but with respect to the 3 areas that I presented before, you could come up with many other questions that you might want to explore. So I think this is very empowering. So I presented you an interesting data set that I thought it was interesting. I've also explained that there's many problems that you could try to solve and many questions that you can give answers to. So now you can formulate an hypothesis. So that was what I called step 3. So let's start with the first attempt. I'm going to pick the simplest problem. So can you predict the rating of a song? Well, this is pretty much a problem for prediction. So you can phrase this problem as a regression problem. You can turn categorical variables into numeric variables, consider all the features, and pick a machine learning algorithm to do the job. So this is pretty much, the bare bones backup to what you want to do. And now you want to pick what is the best tool to solve this problem. Well, because of what I explained to you before, exploratory analysis revealed ratings are highly clustered. We can look at 5 different scores and formulate a problem also as a classification one. And we can split the ratings of 0 to 100 in 5 intervals, and each becomes a class, and we can label these. So I now explained to you we have pretty much a regression problem or a classification problem. So now I get really to the bunch of my talk, which is random forests. So this was a sort of like long-winded way of getting to the point that I wanted to get. But that's pretty much how you go about solving this type of thing. So what are random forests? Well, AKA the best black box method ever. This is actually this is a quite recent algorithm from the 90s, late 80s, early 90s. And it's a highly versatile ensemble method which combines several models into one. So for most people, classification trees are very simple to understand because you have a set of rules, and then you pretty much can predict something from knowing the set of rules. So random forests are built from aggregating trees. They can be used for regression and classification problems. They do not overfit and can handle large amount of features. And they also output a list of features that are believed to be important in predicting the variable. So if you're presented with a problem such as the one that I told you before, well, there's many different machine learning algorithms you can pick. You can even start from a very simple linear regression, and that's a way of solving it. And then you can either pick other type of machine learning algorithms to do this problem. And what happens in real life is that people that are very comfortable with a specific machine learning algorithm will use that for everything. So if you are very into neural networks, you'll probably use neural networks to do everything. If you're into support vector machines, you'll probably use that to do everything. Or, well, not everything, but let's say everything that you can use it for. But random forests are great. They might not be super interpretable, and that's why there's the black box method. But you can never do worse than the other much more fancy methods. So let's do a very small layman's intro. I pretty much stole this from Edwin Chen's blog. It's a post. So he explains random forest in the following way. So let's consider Jamie and Brienne. So Jamie goes and tells Brienne about his favorite movies. And then Brienne is like, oh, cool. So Jamie's like, I like Titanic, and I like, Little Mermaid. I'm a closet Disney fan. And I also like the action movies, et cetera, et cetera. So then Jamie wants to see if, given this information, Brienne can tell Jamie if he will like X movie. So he says, well, I've told you all this stuff about movies, so now would I like X movie that I don't know, I haven't watched? What do you think? So then Brienne starts playing the famous game of 20 questions. So you know the game of 20 questions, where 20 questions would lead you to something that you have to guess. So in this form, Brienne is pretty much the decision tree for Jamie's movies preferences. So these 20 questions are pretty much the different nodes of your decision tree. And then at the end, given these 20 questions, she might be able to tell Jamie, yes, you will like this, or you will like it like that. So now let's get a bit more sophisticated. So instead of just asking Brienne, because there's just one tree, so let's ask Tywin and Cersei and Tyrion. And Jamie gives each of them a slightly different information because, to be fair, if I get very excited, I might go and talk to you and tell you, oh, I like Tolkien movies a lot, Lord of the Rings, yay. But then if I go to other person and I might be very embarrassed because I don't want to come out all nerdy, I'll say, yes, I like them a lot, but I might not be super excited. So there's some slightly difference on information. So then the way in which Jamie tells about his movie preferences to Tywin might be very different to how he goes and tells them to Tyrion or to Cersei. So going about the same procedure, they form a back forest of Jamie's movie preferences. So each of them is a different tree. And because you have this different sort of bootstrapped set, then you have a back forest of Jamie's movies preferences. So now the last point is if Jamie demands getting different questions every time. So the last step was pretty much Brienne playing the 20 questions, but he wants different questions. So if these questions, the selection of these questions is random, then at the end we now form a random forest of Jamie's movie preferences because they're not the same questions. So this is the idea behind random forests. So much more formally, a tree of maximal depth is grown on a bootstrap sample of size m of the training set, and there's no pruning. Then if you pick, under these conditions, you can then start splitting on each node, and you're going to be sampling variables out of this point. And the best split of these variables according to specific criteria that you might define is used to split the node into two subnodes, et cetera, et cetera. Then the final classification is given by majority boarding of the ensemble of trees in the forests. And there's only pretty much two free parameters, the number of trees and the number of variables in the random subset at each node. So now what are these two criteria to pretty much split the node? Well, that depends on the implementation. Different versions might have different criteria. Usually the standard one is the out-of-bag error. So each bootstrap sample not used in the construction of the tree becomes a test set. So you basically just pick some, and then other ones you leave it outside. And then basically the ones that you left outside consider your new test set. So then when you apply this model into the test set, you get some misclassification error, or MSE for regression, and you average over all the samples, and then at each point, you pretty much know where you're going right or where you're going wrong. And then also in this process, you'll get information about variable or feature importance, because you can look at how much the prediction error increases when the out-of-bag data for the variable is permuted while all the others are left unchanged. So you keep changing the different features and see how that error changes with the permutation. So then if you test a specific variable and you get like huge misclassification error, then it's like, oh, go, this is not a good idea. Then I just change it for another one. I see, oh, maybe this is a better idea. So anyway, that is the idea behind randomForest. And then you can move on into different implementations in your favorite language. So in R, there's various implementations in different libraries. Probably the most common is the one in the randomForest library. But then there's other libraries that also have randomForest implementations, Caret, Party, and Big RF. And there's probably much more than I don't know anything about. However, we're going to follow the KISS procedure, keep it simple. And we're going to test various values of n-try and the number of trees, because those are pretty much my two free variables. So I'm going to stick in R with the randomForest package. So I use the randomForest package, 4.67 with R 2.15. The defaults are n equals 500 trees, and n-try equals p over 3 for regression, and squared p for classification. So that's what you get out of the box. And then that I did with R, and then you can try to do the same problem in Python. So for Python, I use the scikit learn 0.14.1, running Python version 2.7.5. And then the computer that I use is pretty much this very old MacBook. I'm still running Snow Leopard. I don't want to upgrade. For the comparison, I know that this is not proper benchmarking, but then again, this is more about me or anyone else going from one language that you're comfortable with and trying to see if you can do the same thing in another language. So I use the training time, look at specific metrics such as R-squared and RMSA for regression, and accuracy and classification. So you follow the standard procedures, splitting data and training and test sets. So for the ME Music dataset, the data frame is this big, lots of columns. There was a bunch of cleansing that was done beforehand. I can give you more details if you ask me. But let's assume that that was sorted and data now looks pretty. So the results for the regression, this computer is rather slow. So I didn't want to use the default of 500 trees because it would take forever to run. So this was just more to compare like how it would work with Python and R. So I picked 60 trees. I tried 100, and then I started at 10. And I used samples of 50,000, given that I had 82,000 rows. This is the standard call for randomForest. These are pretty much the parameters I gave the function. So if you do that and you press enter on this computer, the training time will be 40 minutes for this particular example. But if you, say 10 trees was already over 10 minutes. And depending on the sample size and on m-try as well, m-try I varied it a few, I took several values, but to be fair, it wasn't a huge impact into the RMSE or the R-squared. So I left it as the default in this case. And if you do this, and then you apply your model, you predict the model in the test set, you'll get your R-squared of 0.581 and the RMSE as 14.587, which on its own, they might not mean a lot to you, but let's compare it. Now, let's do the same exercise in Python. So my parameters were 63. 63 is a sample of 50,000. This is pretty much your randomForest regressor. The training time was 3 minutes and 7 seconds on this computer. And this was the RMSE and the R-squared. So if you look at them, they're very similar, but this was super fast compared to the other one. So I guess Python 1, R0. And this is sort of like the rough plotting. So this is pretty much what you get in R. So you have the predicted versus the real one, the actual one, and this one for Python. So it looks very messy. It's a big data set, but that's how it looks like. ggplot2, 1, non-ggplot2, 0. So now we look at feature importance. So you can extract what were the important features for each of them. So this is what you get in R. So these are some of the words, some of the questions that I told you about before. And they're classified according to the increase in the MSE, or basically percentage change, and the node purity using the Gini coefficient. These are some of the questions. And this is how it looks like. So I know that the letter is super tiny, but you can pretty much see that here there's a sharp turn, and over there. So this pretty much tell you more about how important those features are compared to the other ones. And then if you do the same thing in Python, and then you list them, the most top 10 important features according to this randomForest implementation. And the second column tells you how they compare to the R1. So distinctive, which was this particular randomForest top feature, was number 7 in the R1. Catchy was number 3. Like artist was number 2, etc., etc. So they're not super, super different. Just so you can compare, I also did the general linear regression. And then you can also do multiple linear regressions. This ones I did in R. And this is pretty much the RMSE that you get. So you see that's actually quite similar-ish. This is not a randomForest. They're not terrible. So that's how good as it gets. And then if you do the same problem using classification, this is pretty much your confusion matrix. This is for R. Took 8 minutes on training time. The out-of-bag error rate, and the accuracy is 0.567. You can see that it's more or less OK. There's some misclassification error over there. You can do exactly the same in Python. Training time is 2.56 minutes. To be fair, the prediction is faster in R, but the training time is the important one. So that's the prediction, 0.564. The classifier in Python was slightly better. And, well, you can do the same exercise of feature importance. So here the questions somehow were much more considered important. Here are in Python compared to R. So again, the similar set of questions. This is the confusion matrix in R, some cute visualization. And the same thing for Python. So I haven't used the ggplot2 for Python, so I hope it's better. And well, once you do this type of exercise, you can reformulate an hypothesis. And for this, you can determine which features account for most of the variance. You can do principal component analysis. I did this for the words data set. Interestingly enough, you find that the features that have a larger first principal component, distinctive and talented, were some of the features that both the randomForest in Python and in R consider important. So that's nice to know. So you can try to make a simple model choosing meaningful variables. So I choose this ones, given the previous visualization. You can build a randomForest in R and Python. In R, the time of your training decreases a lot, becomes 15 minutes versus what I told you before, that was a long time. And these are the results. If you have the reduced model and the full model, so it's quite crappy on the edges. It's quite good in the center. So, and it seems you didn't lose much by ditching most of the variables. So, well, some comments. It is well known that randomForests have shown to be biased towards highly correlated variables. So using conditional inference trees, you ameliorate that bias. So if you see the party package in R, they'll use conditional inference trees. So one could try to use this implementation to see if you get better results. For scikit-learn's implementation, you have the njobs parameter to parallelize training. So that is definitely better than the standard randomForest library. And for a similar feature in R, you have to look at the big RF package. And then concluding remarks. So the key message of this talk was pick the tool that is best for the job. So we solve a problem using both R and Python via scikit-learn. So there's clearly constraints for addressing a given problem, and they might differ and would dictate the implementation of choice. So for people that are working into pushing, generating data products, maybe doing this type of things is better to do in Python because it's easier to put into the pipeline than if you're doing a standalone analysis, for which R might be better. It's worth learning about both implementations. Both R and Python via scikit-learn implementations have added functions that allow the user to explore the resulting model and its performance. So there's many different methods that you can use on the predict object, and you can get further insights. RandomForests are great. They give great accuracy, can handle many features, does not require cross-validation, and it even estimates what variables are important. And finally, keep an eye out for interesting data. Having data that you're interested in leads to more interesting questions and reasons to explore new methods, add a new trick to your bag. So if you're invested, if you do astrophysics and you're in love with astrophysics, then astrophysics sets are good for you. Maybe not medical ones. And the MD data set is great for test writes. The set has a lot of behavioral information on a subject that everyone has some intuition on. So everyone pretty much knows about music. So you might have some intuition to feed into those hypotheses. And then to do this with Python. Prediction using SVMs and other matrix factorization techniques. You could try to do full factor analysis, etc., and explore the different libraries that Python and R might offer. So thank you. That's all.
So I think the main question is you basically compared the libraries between R and Python, maybe not the languages in itself. So could you say something about the quality of the packages in R versus the ones in like scikit-learn or Python?
Well, of course, this comes from limited experience, and this was very much an approach as to how someone who is quite familiar with one language might try to do the same thing and learn what is done in the other language. I mean, I'm biased towards R because it's what I know. There's just so many libraries, and if you do statistical analysis, there's, again, pretty much everything you ever need is there. But I was very impressed with Python, not only because it was fast, but also because it makes very easy to just plug it into APIs. And in this particular example, not, but in others, yes. In R, it becomes a bit tricky if you're trying, say, to pull web data. So not in this particular example, but in others, you can definitely see how Python, being a general purpose language, might be a tool of choice for specific problems. I mean, I'm very far away from saying if one is better or worse. I don't think you can say that. It just depends on the problem and scope. That's what I wanted. That's the type of message I wanted to get across.
Python is better.